we've been looking at the kinds of transformations we can do with matrix multiplication. So our basic example that we have been building from was a square that was 3 units wide and had one corner at the origin. So we had this square. And as far as describing that square, the corners, the points that describe the corners of the square are actual points. They're not vectors, but we used vectors to describe them so that we could do calculations with the vectors, and that has an effect then on the corresponding point, right? So the point, treat it as a vector, modify the vector, and then we can see the end result of the point itself, right? So it has an effect on the square. So what happened? We've been starting with that point, so we have 0, 0, and then we've been working around in an anti-clockwise way. So if the square that we've been looking at was 3 units wide, and so that was our square. Turn those lights up. This front set. The other way. The on, all on. Top button, I think, isn't it? Yeah. Thank you. Oh, I said on. I'm sorry. So, what kinds of changes were we able to do to this? The kinds of changes we were able to do to this with matrix multiplication, we could do scaling. What? Before we did rotation, we did shearing. Right? We did shearing. And then we talked about rotation. And all three of those we can do with the appropriate matrix multiplication. All right, so in this situation, if we wanted to scale, say, in the x direction, what would we multiply by? Let's say we wanted to make it twice as wide.
2, 0, 0, 1.
Yeah, we multiply by 2, 0, 0, 1. And what would that do? That affects just the x portion and leaves the y portion alone. And the x portion gets stretched. Everything is double what it was before. Well, what happens to the things that are on the y-axis? They stay fixed, and so it just, end result, stretches in that direction. What if we wanted to stretch in just the y direction?
1, 0, 0, 2.
Yeah, we have 1, 0, 0, and then however much stretching we wanted to do there. What if we wanted to do both? We saw if you wanted to do both, you do one and then do the other. So we could have something like A0, 0, 1, and then do the other. And the end result was a matrix that would do both scaling aspects at the same time. All right, so we went through this. We saw how that works. How would you undo the scaling?
Find the inverse. Find the inverse.
Right, we find the inverse of the matrix. And if we have a matrix like this that did scaling in 2 directions, this matrix only has entries on the diagonal, so it's a diagonal matrix. How do we undo that? What is the inverse of that matrix?
For this instance, wouldn't it be like 1 over A and 1 over B?
Yeah, so This is easy to see. If you doubled something, you have it to undo that, right? If you, whatever we do. And so, but if we apply the formulas that we found before, it gives us the same answer as well, right? But the idea here is that we can scale, we can undo the scaling. All right, so that was what would happen in the case of scaling. What about shearing? If we just wanted to shear, what did we do? Let's say we wanted to shear in the x direction. So we had our square, and we wanted it to shear like that.
1, 0, 1.
Yes, if we just wanted to, however much we wanted to shear, we put that value right here, right? So whatever x amount of shear we wanted. So we have the identity and just change that one part. If we wanted that in the y direction instead, then we put however much y shear we wanted up here. All right, and so we looked at different examples to see what happens in different ways. What happens if we multiply by that matrix right there? Stays the same, right? The identity matrix, nothing changes. Rotation, how do we do, say, a 90-degree rotation, a positive 90-degree rotation? All right, so the rotation matrix was cosine of the angle, sine, negative sine, cosine. And what happens, again, this is because we are multiplying with the vector on the left and the matrix on the right. And this would be a positive rotation in this case. What stays fixed in all of these? The scaling, the shearing, and the rotation?
The origin.
The origin stays fixed, right? So that's this kind of situation where the matrix multiplication and the origin stays fixed. That transformation of the vectors, we have all of these are examples of what are called linear transformations. These are the kinds of things that we can do with a matrix multiplication. All right, we said then that motion, translation, is not a linear transformation. Why is translation not a linear transformation? Well, translation means we have to move things. And what happens with a linear transformation? The origin always stays wherever it was. It stays fixed. So if we have to move something, well, you can't move the origin. So what happened when we tried to scale something, for instance, that was over here? When we tried to scale something that was over here, it stretched, but it also moved it. And so things that aren't at the origin, the scaling, the shearing, and the rotation, we have to be extra careful because they don't quite do what it doesn't work in the same exact way, right? Applying the same matrix does not give applying that same matrix does not give the scaling, the shearing, or the rotation that we expect. What would happen if we applied the rotation matrix to this square?
It would rotate around the origin.
Yeah, it rotates around the origin. So it's going to, the square is still going to be out here in terms of the rotation. And so the rotating about the origin, when we say rotate that square, that's probably not what we meant. Okay, so let's think about this square. This square, let's say, is over here. Let's say that corner is at 6, 0. So we're now at 6, 0. What is the next corner? What's this point? That would be at 9, 0. That corner up there? 9, 3. And the top left corner? 6, 3. Is at 6, 3. Right, so if we have this square and we apply one of those matrices, it does other things to it. So let's think about how we could move this square and it do what we want it to do. It actually, applying a matrix multiplication, and it actually move the way we want it to. All right, we can't do this with a two-dimensional matrix, because what happens with a two-dimensional matrix multiplication, we know the origin stays fixed, things don't move the way we want them to. But here's what we can do. Let's imagine that this square lives in a three-dimensional world rather than a two-dimensional world. So instead of this square being on the board here, it is somewhere else in 3 dimensions. Let's think about a problem that we saw early in the term. Early in the term, we talked about the situation of what would happen if we had tables lined up all the way across the room. And we came in the door, and we needed to get to the other side of the room. But the tables are lined up all the way across. We said, okay, well, in this particular room, we could go back out the door and maybe go through the room next door and come in a door that's on the other side. But if that door, say, were locked, we couldn't do that, right? So we're on one side of the room and we needed to get to the other side of the room. If we just look at it as a two-dimensional problem, we can't get there because the tables are in the way. What do we do in real life if we had to get to the other side?
You just go over.
Go over or go under, right? We would just make it to the other side of the table by going over it. Or, again, if it were easier, we could go under. Well, we're going to do the same kind of thing here for translation, for the movement aspect. We're going to think of this as not being a two-dimensional problem, but we're going to think of it as a three-dimensional problem. So we've seen this before, of taking a two-dimensional vector and turning it into a three-dimensional vector so that we could do, for instance, the cross product. We saw times that using the cross product would answer two-dimensional questions for us, but we had to turn those things into three-dimensional vectors to make it work. Well, how did we turn a vector into a three-dimensional vector to work in the cross product? We added a third component, and we made it a zero. Well, that still kept it in the same plane. And what we want to be able to do is to go into a different plane, go out of where we are. And so what we will do in this situation is we're going to turn this two-dimensional situation, instead of in this plane at the level 0 in the third component, we're going to move all of this out here one level further, right? We're out at the z equals 1 level. And so what we can imagine is that we have this shape that is created, and when you look at it from over there, you see just the face. You just see just the square. Now that square is really created by some vectors coming from the origin. But we can think about it, if just for visualization, we have a cube. And the cube is, you're looking down on the top of the cube. So what do you see? If you look straight down perfectly on top of the cube, you see a square. But now what we're going to do is we're going to shear that. Well, what happens when we shear that? Well, as far as the cube is concerned, this is looking down at the top here. There's a square up here. When you shear, you still have the square at the bottom, you have the square at the top. Right? Really what we're looking at is, again, our vectors coming from the origin, but we have that square shape. So if we shear that, what do we still have? We still have a square shape. Does that make sense? And then what we're going to do, we've taken the square in 2 dimensions, put it out here in 3 dimensions, we apply a shear, and then we're going to project that back down. So what do we see? This square was here, and now it's over there. Does that make sense? Let's do a calculation and see what would happen. So, by adding these ones, what have I done? I've taken the square that was here, and now it's living out here. Right? One level further in a plane above that plane. Again, as far as the vectors are concerned, the vectors are pointing from the origin over to that, so to create that shape. And now we're going to shear those vectors. So this matrix is how big?
4 by 3.
It's 4 by 3. And we need to multiply by something that will give us then back another 4 by 3 matrix. All right, because what do we need? We need to describe the top of our object in three-dimensional space still. So it still needs to be a 4 by 3. So how big does this matrix need to be in order to do that?
3 by 3.
This matrix needs to be 3 by 3. Remember, these threes have to match, and then the 4 by 3 in the answer comes from the outside portion. All right, so what we're wanting to do is we're wanting to do a shear that keeps what in place? The shear, let's say we want to move this so that this point right here, let's move it so that this point is at the origin. So the 6, 0, we want to move that corner on the two-dimensional plane. We want to move that to the origin. Well, what are we wanting to do to that in 3 dimension? In 3 dimensions, we're wanting to move this whole thing, shear it so that that shape is out here. So what happens to this point? This point needs to be moved or sheared to 0, 0, 1. Does that make sense? All right, so what would we need to do for a shear, and all we're changing is we want to just change the appropriate x values, right? Because we're just moving things this direction. So we don't want to change anything in the y direction, and we don't want to change anything about the z value, right? That we want that to stay out on that same plane. All right, so what do we do? How do we turn 6, 0, 1 into 0, 0, 1? That's our goal. Let's think about what we have to do. We need this column to be able to pick up the information about the x-coordinate. So how do you pick up the information about the x-coordinate? We can pick up the information about the x-coordinate by putting a 1 there. That will pick up the x value. We want to ignore the y value. Let's put a 0 here. And then what do we want to do? We want this next component to be able to undo that 6. So what do you think? Put a -6 here. Then what happens otherwise? What about the y value?
Y value is 0.
Y value all the way through needs to stay exactly the same.
Okay.
And the third component all the way through needs to stay the same as well. So let's think about our two-dimensional shear. A two-dimensional shear looks like this, only just a 2 by 2 version, right? Three-dimensional shear looks similar to what the two-dimensional problem was. Does that make sense? So let's see what happens. Let's do the calculations. First entry. What do we get? Do the dot product of this first row with this first column. And we get 0. 6 minus 6. All right, what about the dot product there? It's also 0. And this is 1. So we got the first row that we wanted. Well, let's see what happens as we go through the rest of this. What happens here? So we have 9 minus 6, which is 3. This entry, 0, 1. What's going to happen to the second and third entries in all of these? The second column is going to be exactly this, and the third column is going to be exactly this. The only one that involves calculations is the first. What happens here?
3, 3, 1.
Right. What do we have? We have 9 plus 0 minus 6. That's 3.
Yeah.
The next column, zeros and just the 3. And the third column, just the 1. So we get 3, 3, 1. And this entry,
0.
that last row, we get a 0 here because 6 plus 0 minus 6, and then the 3 and the 1. Does that make sense? So that's the calculation at least. Is the calculation okay? Now, what have we done? We took a two-dimensional problem, raised it to 3 dimensions, did our work in 3 dimensions. Now what do we need to do? Now we need to put it back into 2 dimensions. So how do we get from here back to 2 dimensions?
Content is by 2 by 3, or not 2 by 3, 3 by 2.
Okay, so we need to drop the last column is what we need to do. But we can't just drop the last column unless, at least because we're talking about matrix multiplications, right? So what matrix do we need to multiply by in order to get back to, and so we said we're trying to drop the last column. So we have a 4 by 3 right here, and we want a 4 by 2 answer. So we need to multiply by a 3 by 2. What 3 by 2 do we want to multiply by? An identity that just doesn't have that last column, right? So we multiply by the identity matrix the 3 by 3 identity matrix without the last column. And what does the 3 by 3 identity matrix without the last column do? The first part is only going to pick out the x value, and the second column will pick out just the y value. So what do we get? We get 0, 0. And as we go down the list, we get those points. And so this matrix is a projection matrix. It projects the 3-dimensional thing into this particular 2-dimensional plane. And we'll see some other projection matrices if we're projecting things in different ways later on. But this is the first time that we've really seen a matrix that's not a square matrix that we are utilizing in some particular way. All right, so what happens? We start with our square that was here. We raise it to a 3-dimensional world. We shear it in 3 dimensions. and then project it back down to 2, and what happens? What do we end up with? We end up with the square that we started with, exactly in the location that we wanted to move it back to, right? We wanted to move it back to the origin, and this calculation does that for us. Does that make sense? All right, so translation in 2 dimensions can be done with matrix multiplication. But what do we have to do? We have to do that in a 3-dimensional process. This idea of creating these values of ones, notice that this matrix keeps the ones in place, so it keeps us at that next level. These are called homogeneous coordinates. We have put things all in the same location in terms of the plane that they're located in. So they were in one plane. We can't do translation in that plane, but we can give the effect of translation by moving to a different plane, shearing in that dimension, and then projecting back to our original location. All right, so if we want to move something, what do we actually do? We don't actually move it with a matrix that's in the same dimension. We move it by shearing in a higher dimension. And shearing in the higher dimension, end result is movement in that lower dimension. By raising to a dimension, shear, project back down, and what happened? The square was here. Our process was go up here, shear, and project back. So if we draw the picture to begin with, don't draw the intermediate steps and just draw at the end, what happened? The square was here, now it's there. Right? So the end result is that we get motion in 2 dimensions, but it happens by going over the problem. Okay? Now it turns out that the same thing happens in 3-dimensional space. In 3 dimensions, if we want to do translation, again, it fixes the origin, but matrix multiplication fixes the origin, and you can't do that. But if we jump up to 4-dimensional space, in 4-dimensional space, we can then shear in the same kind of way with the ones in place, shear in 4 dimensions, and then project back down to 3 dimensions, and we have the same end result of the thing was here, and now it's somewhere else. All right, so to create the matrix multiplication, or to allow matrix multiplication to create motion or to create translation, we can't do it in the same dimension that our problem is. We have to go up 1 dimension to do that work. And so what we have linear transformations that keep the origin fixed, and translation together with all of this forms a kind of transformation that we call, if we add translation to it, all of this, the term is an affine transformation. So we're not going to worry too much about the details there, and there's some extra aspects to all of this. But an affine transformation is something that we can do with matrix multiplication, but we have to do it in the appropriate way, right? So the matrix multiplication directly, we've seen, can do scaling, shearing, and rotation. Now if we want to do motion, we can still do it with matrix multiplication, but not in the same dimension that we were in originally. We have to add this extra step. And so there's a lot of more details that we could look at in terms of different properties of transformations and different things that can happen. But for our purposes, we have the kinds of things we need to do. We need to be able to scale, shear, rotate, and move. If we want to have some kind of animation, we have to be able to move things. And if we're wanting to do this, say, programming-wise and using matrix multiplication because it's straightforward to implement as far as the programming steps, we have a vector class, we have, or will have, our matrix class. We will have these pieces in place. And if we want to utilize those pieces, we just have to include the possibility of going to a higher dimension, doing work in a higher dimension, and then coming back down. Of course, again, we only try to show the parts that are, we only show the parts that are relevant, right? So we only show the two-dimensional part of the work if we are doing this. We don't try to display the three-dimensional calculations that are happening behind the scene. And the same thing in 3 dimensions. We don't try to display some 4-dimensional thing. Right? We only show the end result, the beginning and the end, and the thing, the object, whatever it is, has moved appropriately. All right, so we have this starting we had this starting square that was shifted over. We've written it so that it works in 3 dimensions. And let's say we want to rotate this square. We want to rotate it about that corner right there, the bottom left-hand corner. If we want to rotate it about the bottom left-hand corner, so if we wanted to, what kind of rotation, how much of a rotation was that? How much of a rotation? 45 degrees. What if we went ahead and just rotated it 90 degrees? That's not 90 degrees. Yeah, there we go. We rotate 90 degrees. So what will happen? We can keep track of where the points were and where they end up going ultimately. Okay, so let's see what happens. Let's try to rotate this 90 degrees. Well, if we just multiply the original 2-dimensional version by the 90-degree rotation matrix, what happens? That's rotating about the origin, not about that point, right? So how do we rotate about that point right there?
Same kind of process we did earlier.
So what do we need to do to rotate about that point? Well, first of all, we need to move that to the origin. So we have this. But then, rather than directly projecting back down, what do we need to do? We need to rotate at that point. Right? So in this situation, we'll remember that matrix. We need to do that again later. But instead of that answer, I don't know why I erased that part. Instead of projecting that back down, we want to rotate. What do you think the rotation matrix for this should look like?
3 by 3?
So it'll be 3 by 3 because we want a 4 by 3 answer. So it needs to be a 3 by 3 matrix. What happens with that 3 by 3 matrix? Well, we still want that rotation to take place in the appropriate position. So how do we do that rotation? How do we do that rotation? If we think about what's happened, we have moved this square over here. It's living out here, away from the, right, in the higher plane. And we want to rotate. What are we wanting to rotate it about? We want it to rotate about that bottom left-hand corner. But we have that vector pointing out through that. We actually want to rotate about that axis, about the z-axis. All right, so how can we do that rotation? What do you think happens to give us that rotation? I mean, one thing we could do is project this back down to 2 dimensions, do the rotation in 2 dimensions, and then what?
And then kind of do some weird, like, translate it back.
Yeah, so then how would we translate it back? If we took this thing, projected it down, back down to 2 dimensions, used our regular rotation matrix, then we would have to project it back up and translate over to put it where it needs to be. And then project back down. Does that make sense? So it would be 2 dimensions, raise it to 3 dimensions, translate, shear, right? This is a shear in the 3 dimensions. Project back down, rotate, back to 3 dimensions, shear again, project back down. Okay, we would like to be able to do that in a more condensed form. So is there a matrix that we can multiply right here, a 3 by 3 matrix, that will do this rotation in the way that we want to? So let's think about our 90-degree rotation. What would the 90-degree rotation matrix that we have? It would be a 2 by 2 that we've talked about, right? So what is the 2 by 2 for 90-degree rotation?
Cosine x, sine x, negative sine x.
So for 90 degrees,
90 degrees, 0, 1, negative 1.
right, so that matrix was 0, 1, negative 1, 0 in 2 dimensions. But what are we wanting to do? We're wanting to affect the x and y coordinates, but leave the third component alone. So what do you think? Would putting this to account for the x and y components, but then leave the third component alone, would that do the rotation that we want? Well, the only thing we can do is try it and see, right? This is good advice as far as programming is concerned as well. We say, well, we know something that works in this case. We're looking at a new situation. What might work? I don't know. Let's try what we did before and see if it works. Right? It worked. The identity columns worked here for keeping things in place. We know the upper left-hand corner portion is rotation in 2 dimensions. Will this work for 3 dimensions? Well, so what's going to happen? We already know that this gives us the desired movement by shearing in the higher dimension. If we do that and then do this, if it gives us the result we want, then we'll we need to still check and confirm. If it doesn't give us the result we want, what do we know? Yeah, if it doesn't give the result we know that we want, then we know that we either miscalculated, so we misimplemented something, or the rotation doesn't work in this way. Right? So we can check and see what happens. All right, let's do this multiplication. Again, going to get a 4 by 3. So what do we get here?
0.
Okay, when we look at that first row, first column, that 0 gives zeros here. Second column, 0. All right, let's go next entry.
0.
That gives us a 0, 3, 1. -3, 3, 1. Zero, 1. All right, so what were we wanting to do? We were wanting to take this shape and we were rotating about that point right there. Right? That was our goal. What have we done so far? What we've done so far is we took that original shape, we moved it to the three-dimensional realm, sheared, and now we've rotated. And what do we have? We think about, we had point 1, we had point 2, we had point 3, we had point 4. What do we have over here? Point 1 is now where? Actually, at this point, it's above the origin, right? But if we scaled back or projected back down, it would be at the origin. So point 1 is here. Point 2, which was 9, 0, is at 0, 3. Well, where is 0, 3? 0, 3 is up here. So point 2 is up there now. Point 3 was 9, 3, and it's now -3, 3. So point 3 is here. And point 4 is now at -3, 0. So point 4 is here. So what happened? It rotated. But it rotated where? We're still over there. What do we have to do to get back to the rotation that we want? Yeah, now we need to move back, right? How do we move this back? We have this matrix M that we're thinking of as it's a shear matrix in 3 dimensions, but for 2 dimensions it's corresponding to movement. So we did a movement, and we've done a rotation. So we started with our shape, multiplied by a movement, multiplied by a rotation matrix. Now what do we need to do? How do we move it back? So we need to multiply by what matrix? So if we multiply by M, what would happen?
Well, no, I mean like something similar to M.
All right, what do we need to do? We need to... Yeah, we need the inverse of M, don't we? We need to undo M. What would the inverse of M look like? What would the inverse of this matrix be? How do you undo a shear?
Oh, 6 on the...
Just put a 6 right there, right? Change the -6 to a +6. Now, again, we could go through the calculation, the formula that we had, or the multiple set of formulas that we have for calculating the inverse. We could do all of that, but in this particular very nice matrix, you undo it by making the -6 a +6. Right? Just like it worked in the shear situation for a small 2x2 matrix, just change the sign of that. Move to the left, okay, we'll move to the right. So what happens? We actually had, I guess, the 2-dimensional version of S that we had to convert to the 3-dimensional version of S, right? So that was going on. Then multiply by M. multiply by the rotation, multiply by the inverse, and then do what?
And then we draw the curve.
And then we multiply by our projection matrix, or to put it back down into 2 dimensions. And what do we have? We then have a matrix with the vectors that correspond to the corners, and they're going to be then in the right spot. Does that make sense? So what do we have? This motion translation we can still do with matrix multiplication, but not the way we could for these other pieces. For these other pieces, we could do all of this still in 2 dimensions. But what do we have to do? We need to translate all of this appropriately. So what do we have? I'm going to get rid of that part because as far as the matrix portion is concerned, if we were writing a program to do this, we might use the projection matrix, or we might modify and actually remove that column. So there are multiple ways we can do that. But what do we do? If we want to rotate this thing about this, we don't necessarily have to do it by multiplying by one thing, then the next thing, then the next thing. What can we do? We could build this matrix ahead of time. I know that this thing needs to eventually be moved over and rotated, so we can pre-calculate this matrix and then just do the multiplication once we have it in place. Not have to do that multiplication every single time. Right? So what would happen if we wanted this square to be rotating about that point? What could we do? We could calculate a rotation that corresponds to how much of an angle we need for, say, each frame. And then just keep applying that same new matrix each time. And so we draw it, apply the matrix, draw it again, apply the matrix, draw it again, right? And keep doing that. Again, what are we drawing? We're just drawing the 2-dimensional portion of it, but we would be able to see this square rotating around. All right, so what would the inverse, what would this look like in this case? So if we take a look at all of our pieces, we have our matrix M. We have our matrix R in this case, which is the 90-degree rotation. And then we want to multiply that by M inverse. What is M inverse? Here's M inverse. And we want to do all 3 of these multiplications and get a single matrix. Well, I guess 2 multiplications, right? All 3 of these matrices multiplied together. Get a single matrix, and then we're going to apply that and that, right? Multiply the original by that, and see if it does the rotation and puts things in the right spot. All right, so what do we have for this portion? Go through. So 0, 1, 0. -6. All right, so the first calculation gives this The next calculation All right, so this says that this matrix is our matrix that will move, rotate, move back. Are we surprised by that? Maybe not. We see the rotation up here. We see shearing happening down here. Okay, but let's apply it to this. Let's see if we get the values that we want. First row, first column. We get 6. So first row is 6, 0, 1. What do we have here?
15.
0 plus 0, that's 6.
So we're going to find
3, 1. Negative 3 plus 6 is 3. So negative 3 plus 6, positive 3. 0, 1. Okay, so this is what we end up with, and then if we project back down, we have just the first 2 columns of that. So let's see what we have. We started with a square that was over here. Had the point 1, 2, 3, and 4. And now let's see what we have. Point 1 is right here. We were wanting to rotate about that point, because that's the one that we moved to the origin, or moved to that location and rotated. So what happens now? Point 2 is at 6, 3. Where is 6, 3? So point 2 is now here. Point 3, which was this one, is now here. And point 4, which was this corner, is now here. And what did it do? It rotated it, right? About that one click, right? So 1, 2, 3, 4 is now 1, 2, 3, 4. Now that wasn't a 90-degree rotation about, like, say, the center. That was a 90-degree rotation about that corner. Does that make sense? What if we wanted to rotate 90 degrees about the center? What would we have to do?
We have to change where we moved it.
Yeah, so what do we do to change where we moved it? We would have to move this center point to the origin, which means we have to do what? We would have to move 2 directions, not just a single. So the M, our movement matrix, wouldn't just be a shear in the x direction. It would need to be a shear,
In the y.
well, in both, right? We need to be able to shear in both directions. So what do you think about shearing in both directions? How would we do that?
Take our shear by the x direction and times it by the shear in the y direction.
Right? Yeah, we would have a matrix that does x shear. Have a matrix that does y shear, multiply those together. But what do we know about multiplying those matrices together like that? Since this one only affects the first column, and the other part only affects the second column, the multiplication looks like that. So to shear in both directions, we can put in a matrix to do this, and then we can do the rotation, and then we can shift back, or shear back, and then...
And so y is the distance?
Yeah, so x would be, in this particular case, we're trying to go to the left, so it's whatever this value is. And y would be how much of the vertical shear we want. In this case, it would be negative as well.
So it's just like how much you move in the y and how much you move.
So if I want...
But it isn't the distance.
Well, it is, because, for instance, if I have the center of this and I want to... And what we're doing is we're moving it, in this case, we're moving it to the back to where the origin is. That's what we want to care about. So how far is it from here to the origin? Well, you have to do it separately in the x direction and the y direction.
No, what I'm saying is it can't be distance because you need direction as well. Because
Right. It's not the distance. It would be, in this case, in this particular picture, we would have negative numbers in those, right? Because we're shifting.
That's what I was saying.
Yeah. So like we saw up here, with this matrix, we were moving to the left, so we had a -6. So what would happen in this point here? It's a negative x value and then a negative y value, because we need to move that over and down to get that to match up.
And so that would be like 1.
Yeah, because this is 3 units high. So that would be 1.5. It would be negative 1.5 here for that particular situation. And what for the other? What would the x be in this particular example?
6.5.
Because the center would be over 1.5 from there as well, because it was 3 units wide. So negative 7.5 and negative 1.5. Big picture makes sense? The big picture is to do translations, we go to a higher dimension. And then we do shearing in the higher dimension and do whatever we need to do, rotation or scaling or whatever, and then we shear back and project down. And the end result is translation with the particular motion that we wanted to have in place. All right, so the two-dimensional version works for linear transformations as long as the origin is part of the shape, or if the origin is part of what we want to have in the calculation. But if we want to have any kind of movement translation, we need to do this in the next higher dimension. So let's see. We've seen how to project back down from 3 dimensions back to 2, or if we were in 4 dimensions, projecting back to 3, or if we were in 4 dimensions and wanted to project all the way back down to 2. We could do that as well. What about the procedure of starting with the square in 2 dimensions, and we want to be able to do a matrix multiplication to push this up so that we're ready for the calculation in terms of the translation step. So how big is our matrix right here? This one's 4 by 2. And our solution over here? 4 by 3. So how big would our matrix have to be right here?
2 by 3.
We need a 2 by 3 matrix right here if we're going to do this. Right, so in a minute, I'm going to ask you to fill in and figure out what matrix goes here. But again, as usual on all of this, if you have any questions at any point in future, let me know. Discord, email. This will be something we'll talk more about. But let's see if we can figure out what matrix goes in here.